Okay, now that I'm done clicking all my buttons here and have this all set, we're going to start talking about acids and bases. So before we get into a lot of acid and base stuff involving calculations, I figured it would be good to go through some definitions. So the first definition here is amphiprotic, and that would be a substance that can behave as either an acid or a base. Now, at this point, you might be asking, what is the definition of an acid and a base? And to that, I answer, there are several definitions that have changed over the years as we have come to understand more about chemistry. So, one of the first definitions is the Arrhenius acid and base definitions, in which an acid is defined as a substance that increases the concentration of hydrogen ions in aqueous solution. And a base, on the other hand, would increase the concentration of hydroxide ions in aqueous solution. And that was a great definition for a while. And then we got the Bronsted-Lowry acid and base definitions, in which an acid is a substance that donates a proton, right, hydrogen ion, to another substance. And then a base, a substance that accepts a proton. Now, these might seem similar, but here, right, we have dropped the definition of hydrogen in aqueous solution or hydroxide in aqueous solution, and we are dealing with the exchange of hydrogen ions or protons. Now, a little bit after that, we get the Lewis acid and base definition here. And this one defines many things as acids and bases, right? Because an acid under the Lewis acid and base structure is an electron pair acceptor, and a base is an electron pair donor. And as a result, things that we traditionally thought of as acids, right, things that have a hydrogen ion that can be given up or put into solution, right, while yes, those will still count as acids, right, many more things count as acids and bases under the Lewis definitions, right? Metals can be acids and bases under the Lewis definition because they will accept or donate electron pairs, right? So we have vastly broadened our definition of what falls under the category of acid and base with the Lewis acid and base definitions. So here, talking about acid and base pairs, right? We say there is a conjugate acid-base pair that forms when adding or removing protons. So removing a proton from an acid forms its conjugate base. Adding a proton to a base forms, as you guessed, its conjugate acid. So let's take a look at this equation here, which we are reacting nitrous acid in water, right? It is dissociating, right? Our nitrous acid here, it is dissociating into nitrite. And this is a ion here, right? That has 3 H's and it has a plus charge. So sometimes in acidic situations, you will see this here, the hydronium ion, written as H3O plus. Sometimes you will just see H plus written. That's a really bad H. A much better H, right? So sometimes you'll just see it written as H plus. Either way, right, this is the component that has resulted in the dissolution of your acid. And so here, right, we can define our acid on this side, and it's reacting with water. So in this case, water is behaving as a base. Right, and then on the other side, we have these two new compounds, right? One that's negative, one that's positive, one that has hydrogen. And so when we look, right, we have our base and acid on our reactant side, but then over here, right, we have the conjugate base of our acid, right, those two. And then for the base, right, we have the conjugate acid. All right, so we always work in these pairs, right? Pair 1 up here, pair 2 down here, where we have an acid and conjugate base in 1, and the base and conjugate acid pair in 2. All right, so you always have an acid conjugate base or base conjugate acid pair in acid-base reactions. Now, this goes along with acid and base strength. And how we define strong acids and bases, these are things that completely dissociate into H plus and anions in solution, right? Or a cation and hydroxide ion if you're talking about base, right? So these are our definitions of strong acid and base, that they will completely dissociate when in solution. On the other hand, as you may have guessed, weak acids and bases do not completely dissociate in solution. As a result, the concentration of H plus, and therefore the pH, is calculated using an equilibrium constant and expression. Hopefully you remember those. So here we have a list of strong acids and bases, and as it says right there, you will need to memorize the list of strong acids and what constitutes a strong base, right? So here we have hydrochloric, nitric, sulfuric, hydrobromic, hydroiodic, chlorous acid or chloric acid and hypochloric acid. There we go. Those are the acids there. And then under bases, what falls under a strong base? That would be alkali and alkali earth metal hydroxide compounds, or at least the majority of them. Now, why this falls into conjugate acid and base as well is that for a conjugate acid, right? So the stronger the acid, the weaker the conjugate base. And vice versa, right? The stronger the base, the weaker the conjugate acid. So strong acid, weak conjugate base, right? Weak acid, strong conjugate base. I'll write that down here. Weak acid, strong conjugate base. All right, and so that is how the conjugate acid-base stuff works with acid-base strength, so that your strong acids have very weak conjugate bases, your very weak acids have strong conjugate bases, and we can talk more about that when we talk about buffer solutions in a future video. So one of the last things, or I guess not last things, but one of the important things that we will start to talk about here in relation to acid-base chemistry is the idea of water and it having a neutral pH, right? So water, amphiprotic, hopefully you remember that term from just a minute ago. It also undergoes autoionization according to this reaction, where at any given moment, small amounts of water are turning into hydrogen and hydroxide ions. So that is going on all the time. And so we write this equilibrium expression, right? Notice there's nothing here under a fraction, right? Because we don't list water, because it is a pure liquid. So we just deal with the concentrations of hydrogen and hydroxide ions when looking at the equilibrium for this. And you'll notice, right, the equilibrium constant for this is very small, meaning there is only a very small amount of hydrogen or hydroxide at any given time. But this is always going on, and it gives us a basis from which to discuss pH. So to calculate the pH, and what we're talking about when we say pH, or really P anything, right, is that we are taking the negative log of the concentration of pH, right? So pH. So if we look again at our equilibrium constant for the autoionization of water here, and we have a kW of 1 times 10 to the negative 4, right? We know that if we take the square root of this, right, we're going to get 1 times 10 to the negative 7, which would be the concentration of both hydrogen and hydroxide. But in this case, because it's pH, we're only concerned with the concentration of the hydrogen ion, right? So we take the negative log of 1 times 10 to the negative 7, and surprise, surprise, it comes out as 7. And so this is how we measure whether something is acidic or basic, right? If the pH is less than 7, right, the solution is acidic, right? So pH of less than 7, or a concentration of hydrogen ions greater than 1 times 10 to the negative 7, it's going to be acidic. And on the other hand, if the pH is greater than 7, right, or having a concentration of less than 1 times 10 to the negative 7, did I say that the wrong way? So pH less than 7, right, your concentration of hydrogen is going to be greater than 1 times 10 to the negative 7th. pH greater than 7, right, is going to be basic. So your concentration of hydrogen is less than 1 times 10 to the negative 7, right? Because this has to remain true, and so if you throw that out of balance, the pH is going to change, all right? So greater concentration of hydrogen, it's acidic. Greater concentration of OH, or lower concentration of hydrogen, it's basic. Okay, pH of basic solutions and other P scales, right? So here, if we look at this again, because all of these things are set relative to the autoionization of water, we can rearrange this to say that, right, the concentration of hydrogen is equal to Kw over the concentration of OH, right, where we relate our pH to the concentration of hydroxide rather than just the concentration of hydrogen, right? And so we can calculate the concentration, or the pOH, right, from concentration of hydroxide, same way, right, negative log pOH, and that will give us some information about our system. And we can also do something where we can figure out the pH or pOH based on the other, because if we take the negative log of everything in this equation that we saw earlier, right, we can come up with this, right? That pH plus pOH is equal to 14 because, right, negative log of 1 times 10 to the negative 14th is 14, right? And since negative log of hydrogen is pH and negative log of hydroxide is pOH, right? When we take the negative log of 1 times 10 to the negative 14th, we get that pH plus pOH equals 14. Right, so if you know the pH or pOH of something, you can figure out the other based on this equation. Now, there will be another one that we look at later on that deals with Kw and Ka and Kb, but I will save that for another video, and right now we'll stop before we get into calculating pH using concentrations and, of course, ice tables. So I'll see you in class.